Let's talk a little bit about how atoms are built and how they are all built the same way. What makes the electron configuration of an atom stable? Energy and stability play an important role in determining how electrons are configured in an atom. There are three rules to consider when writing an electron configuration of an element. An electron configuration describes the ways in which electrons are arranged in various orbitals around the nucleus of an atom. The first rule is the off-ball principle. According to the off-ball principle, electrons occupy the orbitals of lowest energy first. In the off-ball diagram, each box represents an atomic orbital. For now, I'll just use the Bohr diagram to describe what this means. So if we have the Bohr diagram, start filling in the electrons from the lowest energy right here, which would be this orbital on the Bohr diagram, and we would fill the electrons of the atom from the lowest energy up to the highest. So on the off-ball principle diagram, it would go from the bottom to the top. And on the Bohr diagram, it would go from the inside out. The off-ball diagram shows relative energy levels of various atomic orbitals. Orbitals of greater energy are at the higher part of the diagram. Another rule is the Pauling exclusion principle. According to the Pauling exclusion principle, an atomic orbital may describe at most 2 electrons. So using the Bohr model again, if this was an orbital, at most 2 electrons could occupy this orbital, so there could not be 3. And using the box from the off-ball diagram, if we had one S, here was the box. The most we could put in this box, this orbital, would be 2, couldn't put 3. To occupy the same orbital, 2 electrons must have opposite spins. That is, the electron spins must be paired. What that means is, when we have the orbital 1s, the electrons must have opposite spins, and we do that by having kind of like half arrows, where one is pointing down and one is pointing up. Spin is a quantum mechanic property of an electron and may be thought of as clockwise or counterclockwise. So if an electron was in an orbit, one would have to spin this way, and the other electron would have to spin the other way. Using a box from the off-ball diagram, we show this by writing an arrow down, kind of like a half arrow down, and another half arrow up. A vertical arrow indicates an electron in its direction of spin. This is using regular arrows. So an orbital containing paired electrons is written as one arrow going up and one arrow going down. I've also seen them where the arrows, they had half arrows too. The third rule for electron configuration is called Hund's rule. According to Hund's rule, electrons occupy orbitals of the same energy in a way that makes the number of electrons with the same spin direction as large as possible. 3 electrons would occupy 3 orbitals of equal energy as followed below. So what this is saying is, once you have orbitals of the same energy level, they're degenerate. And what Hund's rule is saying is the electrons need to fill the orbitals with the same spin one box at a time. And after the last one is filled, the same spin, we go back to the first one and start pairing them up with opposite spins, like this. So going back to this slide, that's where these boxes are coming from. So from this, there's already 2 energy levels that have been filled, which would be 1s and 2s, 2e. So these are already filled. 3 electrons would occupy 3 orbitals of equal energy. Electrons then occupy each orbital so that their spin is paired up with the first electron in the orbital. Looking at this diagram, you can see how the electrons are filled with each element. Starting off with hydrogen, we have one electron, and then moving to helium, we would have two electrons, so they would be paired up. Lithium would then add another electron, which would go in the second orbital. And jumping to carbon, you can see how with the addition of each electron, it's placed in orbitals of the same energy, or degenerate orbitals, where it has the same spin. Moving from nitrogen to oxygen demonstrates how all the degenerate orbitals are filled with the same spin, and then when we add another electron, we come back and start pairing up the orbitals. So looking at the orbit filling diagram of oxygen, we can see that the 1s orbital has two electrons of opposite spin, which is right here. The 2s orbital also has two electrons of opposite spin, which is right here. Each of the three 2p orbitals has one electron. The remaining electron now pairs with an electron occupying one of the 2p orbitals. So this is filled up. So the 1s orbital is filled, the 2s orbital is filled. One electron goes in each orbit of the same energy, and oxygen has 8 electrons, so it would come back and pair up, occupying one of the 2p orbitals. So in the electron configuration, these are orbitals. The number in front of the orbital type describes the energy, and the superscript describes how many electrons are in the orbital. So if there is one electron, it would be 1s1. If there was two electrons, it would be 1s2, or 1s with a superscript. One electron in the second orbital of the 2s would be 2s1. Two electrons would be 2s2. One electron in the 2p orbital would be 2p1. 2 would be 2p2. 3 would be 2p3. 4 would be 2p4. And this would be the electron configuration for oxygen. So let's summarize what we know. An electron configuration is the arrangement of electrons of an atom in its ground state into various orbitals around the nucleus of an atom. The off-ball principle, the rule that electrons occupy orbitals of the lowest energy first. So what that's saying is we start at the bottom of the energy and we go up to the highest energy when we fill the electron orbitals. The Pauling exclusion principle says that an atomic orbital may describe at most two electrons, each with opposite spins. So each orbital, this would be 1s, this would be 2s, this would be 2p. Each orbital can occupy at most two electrons, so we would put one here. They have to be opposite spins, so we would have to put another half arrow in the opposite direction to indicate an opposite spin. And we would start from the bottom to the top. Spin is a quantum mechanic property of an electron. It may be thought of as clockwise or counterclockwise. So one arrow going up would indicate one direction, and one arrow going down would indicate another direction, or clockwise and counterclockwise. Hund's rule. Electrons occupying orbitals of the same energy in a way that makes the number of electrons with the same spin direction as large as possible. So what that's saying is when we go to the 2p orbital, we would fill this up with electrons going in the same direction because they're the same energy first to make it as large as possible, and then come back and fill the rest with opposite spins. So when we make an electron configuration, we use the off-ball principle, starting out at the lowest energy. We use the Pauling exclusion principle, saying that we have to pair up each orbital with opposite spins. And we use Hund's rule, which says that electrons occupying orbitals of the same energy level must be filled in such a way that makes orbitals with the same spin as large as possible. This concludes Chapter 2.